Hi, welcome to the fourth episode of the Cashscript tutorial series. Today we're gonna use a covenant to create smart contract transactions from inside the Cashscript playground. This will use the new native introspection functionality, which was added last Bitcoin Cash upgrade. We'll also use Cashscript version 0.7.3. This is necessary because if you go to the Cashscript documentation, and head on over to the last major release, version 0.7.0, it says added native introspection and covenants and removed our old introspection and covenant functionality. So you need to be at least on version 0.7.0 to use the new native introspection functionality. The example we'll use today comes from the examples page and it's called Lichos Mecenas. It's a way to do periodic donations like Patreon, and it says instead you can create a peer-to-peer smart contract that allows a recipient to withdraw a specific amount every month. So as we'll see, this time period is configurable, so it doesn't have to be every month, and the contract code is listed here below, so you can just press copy and head on over back to the Cashscript playground. If you compile the contract, you'll see Mecenas and the 4 contract arguments that we have to fill in. I renamed the first to recipient public key hash and the second to funder public key hash because they are both hashes of 20 bytes, and the following 2 arguments are integers. The first, the pledge amount, so how much satoshis can be withdrawn from the smart contract every period, and the last argument is how long a period should be, so the period length as an integer. We're going to test this smart contract on testnet 4. And we'll take a look at the smart contract code first before providing the arguments here. So the first function is receive and contains all the covenant functionality. And the second is a reclaim function, like the one of the kinds we saw before. So it just says who can spend the funds. It says the funder can always reclaim his money if he provides a public key and a signature matching his public key hash. The covenant functionality doesn't only say who can spend the funds, but it says how the funds can be spent, so how much can be withdrawn and where the money has to be sent. So the first line in the receive function is required that the transaction.age is at least the period length, and transaction.age is a relative time lock. If you don't know this, you can always use the documentation. Just search tx.h. It will say tx.h is used to create relative time locks. And before we used tx.time, this is used to create absolute time locks. So tx.h just says, just looks since the last transaction. Then we'll take a look at the following next 2 lines. Here the native introspection is used for the first time, so this is just log time. This is also usable in Bitcoin, BTC, but the native introspection features are unique to Bitcoin Cash. So it says require that the transaction output at index 0, so the first output, has a locking bytecode that is called recipient locking bytecode. And this recipient locking bytecode is constructed the line above. It says the recipient locking bytecode is a function, so locking bytecode pay to public key hash from the public key hash recipient, or the recipient public key hash. How do you know that it's 25 bytes? Well, you can just take a look at this function, locking bytecode public key hash, and then it will give you on the global variables page, locking bytecode public key hash takes a 20 bytes public key hash and will output a 25 bytes locking bytecode. So this is what is used here. So we construct a locking bytecode from this public key hash, and it will be 25 bytes. And then we require that the first output, so the output at index 0, has this locking bytecode. Fair enough. If we scroll down a bit, you'll see that there will be other restrictions placed on the first output. So the first output, the value will be determined. For the second output, the output at index 1, so the second output, the locking bytecode and the value will also be fixed. You can see all the native introspection variables if you head on over to the documentation on the guides, on the covenants and introspection. So currently we're using tx.outputs.locking bytecode, but there's a whole bunch of native introspection functionality. So continuing with the example, here the miner fee is fixed. This is handy to do calculations, and 1000 is a somewhat high amount because you need to take into account that you need to pay at least 1 Satoshi per byte, but the contract won't be 1000 bytes in size. So this is a conservative estimate, which is good. Then you know your smart contracts transactions will most likely be processed in the next Bitcoin Cash block. On the next line, we declare a new integer called current value, and the current value is the transaction input of index this.activeInputIndex, and there we take the value. So what does this mean, this.activeInputIndex? It means the from all the inputs, the input which has this smart contract code, so the active smart contract code. So this way you always have the right input, the input with this smart contract code. Because for example, if you say transaction.input 0, then you're not sure at which input the smart contract will live, because someone might add input at index 0, which can have any amount, so not per se the amount locked in this smart contract. And then we calculate the change value. So the change value is the current value minus the pledge. So remember, pledge is something, an argument that we provided in the contract construction arguments. And then so minus the pledge and minus the miner fee of 1000 Satoshis. Then we continue with an if-else statement. So we have not seen that in other tutorials either, but the if-else just says if there's enough money to create another pledge after this. So if there's more than enough money to create a pledge, just create a normal pledge. But if there is not enough money to create a normal pledge, we just send all the remaining value, just the current value minus the miner fee. Otherwise, if there is enough money to send a normal pledge, send the normal pledge amount, so the normal value of pledge, to the first output, and then we construct a second output. This second output contains the change value. So what is the locking bytecode for this change value? Well, it is not a pay-to-public key hash locking bytecode like before. Why not? Because this is a recurring smart contract. So this will be a not a pay-to-public key hash, but a pay-to-script hash smart contract. Like this. So this will be 23 bytes in size. But instead of using new locking bytecode pay-to-script hash, so we don't provide a script hash, which we could, but we read the script hash from the inputs. So it says the change locking bytecode is tx.input and then of a certain input dot locking bytecode. So again, you read the pay-to-script hash from the inputs, but it could also be provided in the contract arguments. So this is just a cleaner way to do it with native introspection. So this is the second time we used this.activeInputIndex, but another way. So if I were to code this contract, I would probably put a 0 in both cases, but then of course to make sure that the zeroth input is always the input that contains the smart contract UTXO, I would put a new line require that the takes.inputs.length equals 1. So this is another way. You can always check the possible syntax by just taking a look here. So takes.inputs.length. So this should be correct. And then if we press compile again, we'll get a slightly different. Of course, we need to put a semicolon at the end. Okay, so we compiled, because if we change the contract, we also always need to press compile. So now it can only have one input, so an input at index 0. But I think actually this is a better smart contract design than before, this small change. So now we will fill in these 4 boxes to test it on testnet 4. So we need 2 wallets, a wallet for the recipient and a wallet for the funder. So let's make those, a recipient and funder. You can create new wallets by pressing the plus button. And then we need to copy paste the public key hashes. So let's copy paste the public key hash of the recipient and of the funder. Then let's take a pledge amount. So 100 million Bitcoin Cash. 100 million Satoshis is 1 Bitcoin Cash. So if you want to take 0.01 Bitcoin Cash, that's 1 million Satoshis. And for the period, we can, we'll say 100. For testing, it's maybe easier to do just 1 block. So we'll just do 1, but of course in a real life situation, you'd calculate how many days or how many months you would want for your recurring donation, and then we press create. So this is the testnet address, which is the representation of the script, the hash of this script. So on the left hand side, this smart contract script gets hashed, and this hash is this address, which always starts with a P for smart contract addresses. I just recompiled the contract and got a new contract address because I changed tx.h to tx.time. This is because you can't currently set a relative time lock in the Cashscript playground beta. The reason for this is, if you go to tx.time, this is set by default, so no additional actions are required. But for tx.h, you need to set it with a .h function, so in the Cashscript SDK, and it's currently not an option in the playground. Hopefully it will be added soon. So now we'll just invoke the spending function for the receive function, because reclaim is very simple. It's just a pay to public key hash spending function like we did in the first tutorial. So now we need to carefully choose the receiving address and amount for the receive function, because the covenant restricts how we can spend the funds. So because the contract has 5 million Satoshis balance and the pledge is only 1 million, we are here in the else function. So there is a change value left. So we need 2 outputs. The first output is the pledge output with 1 million Satoshis. The second output is the change value, so which is the value of 5 million minus 1 million minus the miner fee, so minus 1,000. So 3,999,000, like this. Now we only need to get the 2 addresses. The first address is the locking bytecode pay to public key hash of the recipient. So it's just this address underneath the public key hash, because it encodes the same information. This, and then the second is the locking bytecode of the change output, so the change bytecode. This is nothing else than the smart contract address we compiled, so we put it here. Then if you want, we can disable the change output. Otherwise, Cashscript might have enough funds with these 1,000 Satoshis to only pay like 400 Satoshis in miner fee and a 600 Satoshi third output, but you can test this yourself. So I'll just disable automatic change output for now and try send. And then we'll see if the transaction information was correct. So if the covenant let us spend the funds. It says transaction successfully sent with a link to the testnet 4 block explorer. We succeeded in spending from this covenant. And if you want to see more covenant contracts, you can take a look at the covenants and introspection guide and try the escrow contract, the last will contract, and then finally the mecenas contract we already discussed. So thanks for checking out the video, and see you in the next one.